Hello, and welcome to this section on soil shear failure. Soil analysis. And objectives, and dive into part one of soil shear failure, tongue twister, for a uphill sliding. So when the anchor is below the foundation. Learning objectives for this section on soil are as follows. First, we want to understand the soil analysis checks. Second, we want to understand the modes of failure here. Third, we want to be able to apply engineering judgment within the technical limitations we have, i.e. lack of data and ability to test soil in a timely fashion, or the finances to test the soil, every site we have. And four, evaluate your site and determine what soil analysis and further testing is needed, if any. So soil shear failure is another check we can perform that becomes relevant when we are sharpening the pencil on calculations and begin to get closer to our true failure by including sidewall friction, bottom slope effects, undisturbed soil weight, and more tips and tricks we've discussed previously and more things we'll discuss before the end of the course. A soil element can fail, like any element, under normal stress or shear stress, is bearing capacity, and shear stress are parallel to the soil mass, causing sliding or slippage. Bearing pressure is already one of the checks described in the basic design course. So in this section, we are concerned about that small section of soil from the anchor to the foundation tier failing horizontally. And that can be seen with what I'm filling in with red here. So imagine those forces on the anchor pulling in this direction. And as I mentioned in previous videos, to explain the transformation of bottom slope effects, I explain it as a reaction force from this soil slope. Well, that force can cause the potential shearing of this red section of soil off, which is a mode of failure for the bridge. Now, the strength of the soil to resist shear can be taken from the following equation, found in a study we've talked about, but linked again on interfacial friction. Tau F equals C plus sigma N, or normal stress, times tan phi. Here, C, or the cohesion of the soil, is taken to be zero, because we'll assume our soil is cohesionless, which is, again, a conservative assumption. Phi is our angle of internal friction, which we take as 30 degrees, per usual. Sigma N is our normal stress on the soil, so how much force is pushing down on that block of soil. For our purposes, because the soil is cohesionless, we can multiply both sides of the equation by unit area and find our shear strength in kilonewtons. So if we multiply by area meter squared, we can get some force, some force F, or some capacity soil is going to equal R times tan phi. And then this makes sigma N a little vertical load on the soil. And remember, this is including the weight of the soil itself. And ultimately, we'll want to take that term, multiply by our 1.5 factor of safety, and compare it to RS, which you should remember as the sliding force on the. So, is this sliding force here our ability to resist that will be soil shear strength FF. And remember, we've already calculated this FV value here, but we'll also need to add the weight of the soil. That'll give us a little extra capacity here. So FV is going to be our vertical plus our volume of soil times the density of soil. Now, in order to even further sharpen the pencil on this soil shear failure analysis, it is okay to use greater values for phi in this case. So sometimes we'll use a greater than 30-degree value to make this check work. And this is an engineering judgment decision. This should be okayed and discussed with your DEIC before using a value of 33 degrees or even up to 35 degrees.